I have a question from the last class.
Yes, go ahead.
So in the notes that you have uploaded on the Google Drive,
Hmm.
so on page 3 you have written that dy1 up to dyn is a basis of tfn, where y1 up to yn are normal coordinates near fp.
Right, right.
So it shouldn't it be dy1 up to dyn a basis of tfp star n?
Oh, sorry. Yeah, TFP started. Yeah, yeah. Sorry.
Yeah, yeah,
Right, right. Yeah, sorry. Yeah,
yeah. Thanks.
yeah. Yeah. That's a typo. Yeah. Yeah. Okay, so uh, let's start. Uh, so today we'll start talking about the harmonic maps heat flow, right? So here we have two closed Riemannian manifolds, M and N. And we have F from N to N, at least a C2 map. And then we want to solve the following initial value problem. Or for short, we'll just call this the IVP. So the harmonic maps heat flow is, you want to find U from M cross 0 infinity to N such that it satisfies the following two conditions. So it's a solution of the harmonic maps heat flow. That means that del U del T. So what happens if you differentiate U with respect to T? That will give you a vector field along U at time T, right? Yeah. And this vector field along U, this should be equal to the tension field of U at time T. Okay. So, well, I'll just write tau U. It's understood the tension field is only acting in the space variable. So, okay. And so this is for xt in M cross 0 infinity. And at time 0, you want U of x0. The initial value should be f of x. Okay. So it's like the initial value problem for the heat equation, except instead of the Laplacian, which is a linear operator acting on functions, here we have this nonlinear operator, the tension field, acting on maps. Okay. Is this clear?
Yes,
So
sir.
it's like a nonlinear heat equation. That's all. Right. And this was motivated by looking at the energy function on the space of maps from M to N, right? And looking at the first variation of energy, that gives you a formula for the derivative of the energy in terms of the tension field. And that formula you can interpret as saying that the tension field is the gradient of the, or is minus the gradient of the energy function on the space of maps, right? So the heuristic is that you have this X, which is the space of maps from M to N. So you think of this as some infinite dimensional manifold, right? And then on this space, you have the energy function, which is like a height function, okay? And then you have critical points of the energy function. So there's a critical point here, there's a critical point here, there's a critical point here, and there's a critical point here. So these critical points these are points where the so-called gradient of the energy, that's, or minus the gradient, which is the tension field, is 0. Okay. Okay, so this tension field you think of as a vector field on this infinite dimensional space. Okay, so in this infinite dimensional space, you're going to move along the direction given by the tension field. All right. So this tau you think of as an element of chi x. So all this is in inverted commas. Okay, none of this is not really a manifold and so on, but you think of it like one. Okay. All right. So our heat equation is just, the solutions are, you think of them as integral curves of minus grad E, right? So this is tau of ut. Okay. And the idea is, for the gradient flow on a closed manifold, the solutions converge to critical points. So here, similarly, on this infinite dimensional object, you want solutions of this heat flow, this harmonic maps heat flow, to converge to critical points of the energy. Critical points of the energy are exactly harmonic maps, right? Okay. So these points here, these are all the harmonic maps. Okay, so one would hope that first of all, the solution to this exists and is defined for all time, and as time tends to infinity, it converges to a harmonic map from M to N. Okay. Is the idea clear? Yes?
Yes, sir.
Okay. So the first thing to understand is that suppose a solution exists for all time. Later, we will prove that actually a solution always does exist for all time if N has non-positive sectional curvature. Okay. But first we're going to assume that a solution exists and then show that if a solution exists for all time, then it must converge to a harmonic map. The limit can only be a harmonic map. Okay. So for that, we're going to assume the following. This is a key assumption. So we'll work throughout with the following assumption, that N, the target manifold, has non-positive sectional curvature. Okay, so this is a very important assumption. All right. And we'll see where it's used in many places, but immediately it will be used in one place now. So let ut t in 0 infinity be a solution of the harmonic maps heat flow. So del ut del t is equal to tau ut. Okay. So now so we have the energy density of ut. So this is half norm dut squared. Okay. And we'll define another function, kappa of ut. This is half the norm squared of del ut del t. Okay. So this is also equal to, since ut is a solution of the heat flow, this is also equal to half the norm of the tension field squared. Okay. So let's look at the energy of the solutions. So we have energy of ut is the integral over m of the energy density EUT d vol m. And by the first variation formula for energy, the derivative ddt of the energy of ut this is minus the integral over m of the variational vector field of the variation. So that is the time derivative del ut del t with the tension field of ut, right? This is the first variation formula. Yes? Yes. Yes.
Yes, sir.
Right. This is just the first variation formula. Okay. But now you can put tau ut is equal to del ut del t. So this becomes minus integral over n of norm del ut del t whole squared. Or, well, or you could also put it to be either it's the same thing, minus norm of the tension field, tau of ut squared t vol m. So this is less than or equal to 0. Okay. So let me define another function. Capital K of ut. This is the integral over m of this little kappa. So this little kappa is basically, you think of it as kinetic energy, right? It's half into this del ut del t squared. It's the velocity squared, norm squared of the velocity. So this you think of as a kinetic energy. And this capital K is the total kinetic energy. So this is the integral of kappa of ut d vol m. Yeah. So yeah. So what we're getting here is this is minus 2 times capital K of ut, and that is less than or equal to 0, right? Because this integral is greater than or equal to 0. So we see that the energy is monotone decreasing along a solution, right? So T goes to energy of ut is monotone decreasing. Okay. So from that, you can already draw one conclusion. The energy is decreasing and it's bounded below by 0. Therefore, the limit of the energy exists, right? Even if you don't know whether the solutions converge, you know that their energies have to converge, right? Okay. Yeah. So the energy tends to a limit along a solution of the heat flow. Fine. So now what we want to do is some calculations, and we want to compute the second derivative of this energy. Okay. So for that, we need to compute so what is the second derivative of the energy going to be? This derivative of the energy this is minus the integral of twice the kinetic energy kappa of ut, right? D vol m. So by differentiation under the integral sign, the second derivative is going to be minus twice the integral over m of del del t of kappa ut, right? Okay. So we need to work out what is this time derivative of the kinetic energy, yeah, of kappa. So let's work that out. So del del t of kappa ut, this is del del t of half norm tau of ut squared, right? So by metric compatibility, this is inner product of tau ut with itself, right? So by metric compatibility, what will I get? This will be twice the derivative of this norm squared will be twice the inner product between the covariant derivative d del t of tau ut inner product with tau ut, right? Okay. Yes.
Yes, sir.
Okay. So now we need to compute this. Okay. So so how do we compute this? So what is tau ut? Tau ut, that's the tension field. So this I can write as sum over I. It's a trace, right, of the second fundamental form. And the second fundamental form is given by the second derivative along geodesics, right? So this I can write as, so let me just write this directly. So d del t of tau ut, this is d del t of the sum over I of d del s of del del s. So both of these are at s equal to 0, at s equal to, so no, this one is d del s equal to 0. This one is without. Yeah. So del del s of ut of gamma I of s. Okay. Where gamma i's are geodesics such that gamma I of 0 is p for all I. So these are geodesics passing through a point P, and gamma I prime 0 is EI, where EI is an orthonormal basis of TPM. Okay. Right. So this is the tension field. Yes. It's the sum of these second derivatives over an orthonormal basis. Right. Okay.
Yes, sir.
So now I take this d del t inside, right? So I have d del t, then d del s equal to 0, and then del del s. Okay. Ut of gamma I of s. Now what do I want to do? I have these two s derivatives and I have one t derivative. What I want, what we would have done in Euclidean space is simply interchange these derivatives, right? I would have taken the t to the beginning and the two s's outside. But in this Riemannian setting, I have to be careful because these are covariant derivatives. So for example, when I interchange the first two covariant derivatives, d del t and d del s, I'll pick up a curvature term, right? So this I can interchange the first two. This will become d del s at s equal to 0, d del t, and then del del s, okay? Ut compose gamma I first. But then I'll have to add a curvature term, right? So I'll get a sum over I. So this d del t, d del s minus d del s, d del t, that is exactly the curvature R of del 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 S, del del T. Okay. So what I'll get is R of, so this is the curvature of N coming here, right? So Rn of del ut composed gamma I so del del S of this at S equal to 0. And then I'll have del ut del T. Here I have to put S equal to 0, right? So this is just del ut del T of P. Okay. And then I have acting on this this vector field along this parametrized surface. This will be acting on del del S. S equals to 0 of ut composed gamma I. Is this okay? Yes?
Yes, sir.
Okay. And now here in the first term, this d del T and del del S, by the property of parametrized surfaces coming from the symmetry of the connection, I can interchange this d del T and this del del S, right? These two I can interchange. So that's will bring me what I want, which is I have my my space derivatives, sorry, in front. So d del S at S equal to 0 of d del S and then del del T, right? Okay. And then here I have this sum is, so del del S at S equal to 0 of ut composed gamma S, that is by the chain rule, that will be dut of gamma I prime 0, which is EI, right? So this is dut of EI. And then here I'll have just the time derivative del ut del T. Okay. Or I can write it as tau of ut also. So let me do that. Yeah. So this time derivative by the heat equation, this is tau of ut. And then outside here, I have again dut of EI. Okay. Right? Yes. Okay. And so this first term is what? This del del T of ut composed gamma. This will be again, this del del T of ut is just the tension field, tau ut. And then I'm taking two space derivatives in the direction of EI, right? So this will be sum over I, nabla EI of tau ut. Is this clear? Yeah. Plus sum over I, Rn of dut EI, tau ut, dut EI. All right. Yes. Is this clear?
Yes, sir. Yes, sir.
Okay. Okay. So here I'm abusing notation slightly. My EIs, first of all, were just tangent vectors at a point. But here what I mean is I've extended them to vector fields in a neighborhood of P, which are orthonormal at each point in the neighborhood of P. Okay. So they are an orthonormal frame field. All right. So here EI is an orthonormal frame field near P, such that I can assume this, that gamma i's, each geodesic gamma I is an integral curve of EI. Okay. All right. Yeah, remember how you get such a frame field? You take the basis at the point P, and then you parallel transport this basis along all directions passing through P, right? Okay, that gives you a frame field. So in particular, when you parallel transport along the directions EI, starting at P, that means you're just parallel transporting along gamma, right? Gamma I. And so EI, when parallel transported along gamma I, it just gives you gamma I prime. In other words, gamma I is an integral curve of EI. Okay. Is this all right? Yeah.
Yes, sir.
Okay, so that's why this second derivative here, d del s, we're differentiating along the curve gamma I of s. That's why this becomes a second covariant derivative, nabla EI of tau. Okay. Is this clear? Yeah. Yeah, when you take del t, that gives you tau of ut, and then I'm differentiating twice in the s direction, right? I mean, in the EI direction. So that will give me nabla EI. Okay. All right. Is this clear? Yeah.
Yes, sir.
Okay. Now, now let's look at the Laplacian of the kinetic energy. Okay. So what is this? So this is the trace of the Hessian, right? So this is sum over I. So what is the Hessian? So it is nabla EI of grad kappa inner product EI, right? Yes, this is the Hessian acting on EI.
Right.
Yeah. Now this I can write as so this I can write as EI acting on the function grad kappa inner product EI minus, by the metric compatibility, grad kappa inner product nabla EI. Right? Okay. Yes. This is just by the metric compatibility. This term I can assume is 0 at P, right? Yes.
Yes.
Okay, by hypothesis, by choice of EIs. Okay, we always assume this to simplify calculation. Okay. All right. So we always choose the EIs so that their covariant derivatives at P vanish. All right. That's it. Okay. So then this becomes just this first term. The second term is 0. And so this term I can write as EI acting on. So this grad kappa inner product with EI is nothing but the derivative of kappa acting on EI, which is nothing but EI acting on the function kappa, right? Okay. Yes. Okay. So we have this computation. We're looking at the Laplacian of the kinetic energy kappa. So this is the sum over I, EI of kappa ut. And now I write what is kappa. So because ut is a solution of the heat flow, this kappa is half, well, it's half the norm squared of del u del t, but del u del t is the same as tau ut. So this is half the inner product of tau ut with itself. Okay. And so now when I take EI applied to this by the metric compatibility, when I apply the first EI to this, I'll get half times 2 times nabla EI of tau ut, inner product tau ut. So this gives me EI of nabla EI tau ut, inner product tau ut. And then when I apply it again, I get a term that I had above. I'll get inner product. So again, by the metric compatibility, nabla EI, tau ut, inner product tau ut, plus the sum over I, so I'll get nabla EI tau ut, inner product nabla EI tau ut. So that's norm squared of nabla EI tau ut. All right. So I get this, okay. So there's a sum over I here. So sum over I, nabla EI tau ut, inner product tau ut, plus this second term I can just write as the norm squared of nabla tau ut. All right. Is this clear?
Yes, sir.
Okay. So now let's try and recognize this first term here. This also appeared in our earlier computation where we computed the covariant derivative d del t of tau ut, right? This term comes up here. And if we go back further, our derivative of the kinetic energy, this is what we want to compute. This is inner product of d del t tau ut with tau ut. So this d del t of tau ut we computed below, right? So we substitute that here. So what are we going to get? So now we get the following, that del t of kappa ut, this is inner product of d del t tau ut with tau ut. So this we've computed, the first term inside the inner product. So this is going to give me a sum over I, inner product nabla EI tau ut, inner product tau ut, plus there was a curvature term, right? So I'll get a sum over I, inner product Rn dut EI tau ut dut EI, the whole thing inner product with tau ut, right? Yes? right?
Yes, sir.
Okay. Now this first term here, this appears in the Laplacian of kappa ut. So this first term here, this is the Laplacian of kappa ut minus the norm squared of grad tau ut, right? Okay, plus I have these curvature terms. Okay, so these are sectional curvatures, if you like, multiplied by norm of a wedge squared. So, yeah, so this is Rn dut ei tau ut dut ei tau ut, right? Now, because the sectional curvature of n is non-positive, this inner product, all of these are less than or equal to 0, right? Because the sectional curvature of n is non-positive. Is this clear? This is a sectional curvature times the norm squared of the wedge product of dut ei with tau ut, right? Yes?
Yes, yes.
Right? So this is less than or equal to 0, okay? And so the whole thing, what we get is that this is less than or equal to Laplacian of kappa ut, right? Okay? Yes?
Yes, yes.
Okay. So thus, if I look at the second derivative of energy, what do we find? So from the first variation formula, well, so we found that this was minus 2 times the integral over m of del kappa ut del t, right? D vol m. And this del kappa ut del t is less than or equal to the Laplacian. So minus it will be greater than minus the Laplacian. So this is greater than minus 2 integral over m of Laplacian kappa ut, right? D vol m. And this is equal to 0 by the divergence theorem because boundary m is empty, right? Yeah, the integral of the Laplacian over any closed manifold is 0, right?
Yes, yes.
Because what is this? This is the divergence of grad kappa, right? So by the divergence theorem, it's the integral over the boundary, but the boundary is empty. This is 0. Okay. All right. Yes.
Yes, yes.
So what do we get? We get that the energy is actually a convex function along solutions of the heat flow, right? If the sectional curvature of n is non-positive, right? Yes? Okay. All right.
Yes, sir.
Yeah, makes sense.
So what do we have? First, we have that ddt of energy ut, this is negative, less than or equal to 0. Okay. So, yeah. And secondly, d squared dt squared of energy of ut, this is greater than or equal to 0. So this implies that ddt of energy ut, this is monotone increasing, right? Yes? Yes?
Yes, sir.
Yes.
Yeah,
Yes.
so if I look at the first derivative, ddt of the energy, this is increasing and bounded above by 0. So therefore, 1 and 2 imply that the limit let me call it, say, alpha. This is the limit t tends to infinity. Ddt of the first derivative of the energy. This exists, right? Yes?
Yes,
Yes,
yes.
yes, yes.
It's just your baby and a real analysis, right? Monotone function bounded above, limit exists, right? Yes? So,
Yeah, yeah, yeah.
so this is also the soup, right? For a monotone function, it's just going to be the supremum. The limit is just the supremum, right? Yes? Okay.
Yeah, yeah, yeah.
Yes.
And the supremum is less than or equal to 0 because the function is less than or equal to 0. Okay?
Yeah.
Right? Fine. So thus we get d e ut dt. This is less than or equal to its supremum, which is alpha. So this is less than or equal to alpha for all t, right? Yes?
Yes, sir.
So, so what does this mean? This means that the energy of ut this is less than or equal to the energy of u0 plus alpha t, right? For all t positive. Yes?
Yes, sir.
Yeah, just by the fundamental theorem of calculus, integrate both sides, you get this, right? So, but on the other hand, this energy of ut, this is greater than or equal to 0, right? So that means that energy of u0 plus alpha t, this is greater than or equal to 0 for all t. But alpha is less than or equal to 0. So if alpha is strictly negative, then this left-hand side tends to minus infinity, right? That's a contradiction. Okay. So alpha has to be 0. Okay. So you can see that also like this. You just take this to the other side. So alpha is greater than or equal to minus energy u0 divided by t. And this tends to 0 as t tends to infinity. So that implies that alpha is greater than or equal to 0, but we already have alpha less than or equal to 0. And so alpha is equal to 0. Yeah. So what I've done by this formal proof, actually, if you think about the picture, it's very easy. You're looking at the graph of the energy function as a function of time. So here is time, t. Here is the energy. So what do you know about the energy function? First of all, it's non-negative. So it's non-negative. Secondly, it's decreasing, right? We saw that it's decreasing. And thirdly, it's convex. So it's convex decreasing, right? So the first derivative is less than or equal to 0, increasing. So it has to converge to some value, right? Now, if that value was some negative number, alpha, strictly negative, then what would happen? Then if I look at the tangent line, that would be a line with slope alpha, right? And the I know it wouldn't be a line with slope alpha. That's not right. It would converge to alpha. So the slope would be less than or equal to alpha, right? So then it would decrease at least as fast as the line segment, right? With slope alpha. So it would have to tend to minus infinity. Is this clear? From the picture, if the limit of the slope is negative, then this would decrease to minus infinity. That's a contradiction, right? Because the energy is non-negative. Is this clear?
Yes, sir.
Yeah, so that's what we've proved here. Okay, that the slope, so this can't happen. So the slope has to tend to 0. Okay, so it has to look something like this. So, you know, the energy also converges to a limit because it's monotone decreasing and bounded below, right? So this is that limit, if you like, E infinity. And the slope has to tend to 0. But now the slope is what? So thus, ddt of the energy. So this, remember, this was minus the integral of norm tau ut squared. So this tends to 0 as t tends to infinity. Right? So what are we seeing? We're seeing that the integral of the norm squared of the tension field tends to 0. In other words, the tension field is going to 0 in L2, right? The tension field is going to 0 in L2, right?
Right.
Okay. So that is enough for us to conclude the following proposition. Let ut be a solution to the harmonic maps heat flow. So here I'm always assuming that the sectional curvature of N is non-positive. So then we have the following. So if for some sequence of times tending to infinity, Tn tending to plus infinity, we have Utn. So let me write this below. We have Utn converges to U infinity in C2 of Mn for some U infinity in C2 Mn. Okay. Then U infinity is harmonic. Then tau U infinity is 0 and U infinity is smooth. C infinity harmonic. So any limit of the harmonic maps heat flow, if it converges in C2 norm, so that means uniformly in C2 norm on M. Okay, so you might be asking, how do I define C2 norm? Well, what you have to do is take charts on M and N. Okay, and then with respect to the charts, you get maps from Rn to Rm, and there you take the C2 norms. Okay, and then you sum over the charts. So that will give you some C2 norm on maps from M to N. And you can check that the topologies you get on the space of C2 maps, these are independent of the choice of charts. Okay. The C2 norms will differ by constants. They're bi-Lipschitz to each other. Okay. This is not so. So yeah, I don't want to define this explicitly, but you understand that there are, so this means uniform convergence in C2 norm. All right. The maps and their first and second derivatives all converge uniformly. Okay. So what's the proof? The proof is very simple. If the convergence is in C2 norm, then that means the second derivatives converge uniformly, right? And the tension field therefore, it's a sum of second derivatives that will converge uniformly to the tension field of U infinity, right? So then tau of UTN converges to tau of U infinity uniformly on M, sorry. Okay. So thus, by uniform convergence, the integral of norm tau UTN squared converges to the integral of norm tau U infinity squared. Okay. But by the above work that we did, the integral of tau UTN squared this we showed converges to 0, right? The tension field goes to 0 in L2. So this converges to 0. So that implies that the integral of tau U infinity norm squared, this is 0. And so that implies that tau U infinity is 0. Okay. This is identically 0. And so by the result that we proved last time, since tau U infinity is C2, U infinity is in fact C infinity, right? And that's it. Okay.
Yes, sir.
All right. So we've proved that if you have a solution to the harmonic maps heat flow, if some subsequence converges in C2 norms, then the limit has to be harmonic. Okay. So in particular, if the whole sequence suppose converges in C2 norm, then the limit has to be harmonic. All right. Is this clear?
Yes, sir.
Any questions? Any questions?
No, sir.
Okay. So now let me tell you what is the goal that we're going to try and prove. The idea is you want to show that some subsequence at least converges. So first of all, you want to show that the heat flow exists for all time. So that's something we're going to show. That will take some work. But once you've shown that, the main point is to show that you have a subsequence like this which converges in C2 norm. Okay. And so for convergence in C2 norm, what you need is that the second derivatives should be equicontinuous, right? By Arzela-Ascoli, if the second derivatives are equicontinuous and uniformly bounded, you need them to be uniformly bounded and equicontinuous, right? The second derivatives. So then some subsequence will converge in C2 norm. Is that clear?
Yes, sir.
Right. And then you will get a harmonic map. Okay. Then you will get a harmonic map. Yeah. And the point is this harmonic map will not just be any harmonic map. It will be homotopic to the initial U0, right? Because, I mean, UT is homotopic to U0 for any t, right? And so what happens is if UT is uniformly close to U infinity, if it's within a small epsilon of U infinity, then one can show that if you have two maps between closed Riemannian manifolds, then if you take an epsilon small enough, it depends on the injectivity radius of the target manifold N. If you're smaller than the injectivity radius, then these two maps will be homotopic. Okay, so for T large, UTN will be close to U infinity, uniformly close, and that will imply that UTN is homotopic to U infinity. And so therefore you'll get that U infinity is homotopic to U0. Okay, so that would have proved what's called the Eel-Sampson theorem. That is, well, any continuous map from M to N, where N has non-positive sectional curvature and M and N are both closed, any continuous map is homotopic to a harmonic map. Yeah. So what you would have to do is first, you take your continuous map, you homotop it to a smooth map. That you can always do. You can homotop it to a smooth map. And then the smooth map, you let that be U0. And then you have a solution of the heat flow starting from U0. And then you have a subsequential limit, which is U infinity, which is a harmonic map. That is homotopic to U0, which is homotopic to F, your initial continuous map. Okay, so that's roughly the proof of the Eel-Sampson theorem. Is it clear?
Yes, sir.
Okay, so that's the goal of that's the main goal of the course from now. So there's a lot of work to do. The first work is to reduce the so the first step is to the first step is to show short-term existence of the heat flow. Okay, so short-term. So we want to show that at least a solution exists for some time 0 up to epsilon. Okay, so that's the first step. The first step is short-term existence. Right, it's just like when you are working with ODEs on a manifold, or the ODEs in Rn, you prove short-term existence first, right, for the ODE, and then you try to prove long-term existence, right? So the first step is to prove short-term existence of integral curves. So we're going to prove first short-term existence of solutions to the harmonic maps heat flow. Okay, so for brevity, I'm just going to call it the heat flow, okay? It's understood, it's the harmonic maps heat flow, okay? All right. Okay, so all right, so the first thing we have to use is a theorem of Nash. We want to reduce things to a PD taking values in Rn. Okay, so for that we use what's called Nash's C infinity isometric embedding theorem. So it says the following, let M be a closed Riemannian manifold. Then there exists a positive integer Q and there exists an isometric a C infinity, there exists a smooth, there exists a C infinity isometric embedding I from M into RQ. Okay. So what does this mean? This means that I so embedding means that I is smooth of full rank. So its derivative is injective everywhere. So here this Q is greater than or equal to the, is strictly greater than the, this is greater than the, than N, let's say. So N is the dimension of M, okay? Yeah, so I is C infinity of full rank. So that full rank means that the derivative is injective everywhere. And is a homeomorphism onto its image. Okay. Which is a compact subset of RQ. So the image is going to be a submanifold actually of RQ. Okay. And secondly, the isometric part means that this map I preserves lengths of tangent vectors. So inner product, it preserves inner product. So inner product of DIP V, DIP W. So this inner product is in RQ. These are vectors in RQ. This is equal to inner product VW. So this inner product is in TPM. It's the Riemann coming from the Riemannian metric. This is for all VW in TPM and for all P and M. Okay. Okay. So the main part is the second part, this isometric embedding. Just an embedding into Rn follows from Whitney's embedding theorem. Okay, that you might have seen already, right? Okay. So any questions? Someone was asking something. Is this okay?
Yes, sir.
Yes, sir.
Okay. So this is a highly non-trivial theorem. It's an amazing theorem. I mean, it's an amazing theorem. Yeah. So it's a highly non-trivial theorem. Okay, so any Riemannian manifold, closed Riemannian manifold, you can realize as a submanifold of Rn with the induced metric. Okay. Yeah. Okay. So what we're going to do is, so now, given M and N closed Riemannian manifolds, you let I be an isometric embedding of the target. Okay. Okay. So we're out of time. Let me stop this session and start a new one. Okay. Okay. So let's continue. So now we're going to think of N, the target, as embedded inside RQ. Okay. So now we have what's called the tubular neighborhood theorem. Which says the following. So I look at my embedded submanifold. So this is a I of N inside RQ. This is my submanifold. Okay. So now at each point, I have the tangent space, which is a subspace of. So if I take a point, say Q here, right? So I have the TQ of IN, the tangent space to this submanifold, and I also have its orthogonal complement, right, in Rn. So this is TQ IN perp. So we define what's called the normal bundle. Okay, so T of IN perp, this is defined to be the set of pairs Q comma V, or say Q comma W, such that Q belongs to I of N and W belongs to TQ IN perp. Okay, so this is a subspace of RQ. All right. Oh, I'm using Q in two places, but don't mind that. All right, it's just an abuse of notation. Okay, one Q is the dimension, the other Q is the point. Okay, fine. So so this is called the normal bundle. Okay, All right. And then you can look at, let's say, U epsilon, which is an open subset of this normal bundle, where you take all vectors in the normal bundle of norm less than epsilon. Okay. So the tubular neighborhood theorem says for epsilon small enough, the map. So there's a map from this normal bundle to a neighborhood of the submanifold. The map is very simple. You just take so let me call this map, say, phi. So this goes from U epsilon to a neighborhood n tilde of the submanifold I of n. Is just Q comma W goes to Q plus W. Okay. So this map is a diffeomorphism onto a neighborhood n tilde of I of n in RQ. Okay. Yeah. So that means that any point in this neighborhood, say a Z here, I can write as W plus, Q plus some vector W, which is perpendicular to the tangent space. Okay. So this vector here, this is W. All right. Is the picture clear? Yeah. So this neighborhood will be a two-sided neighborhood like this. So this is your tubular neighborhood, this inside and this outside. This is your neighborhood n tilde. Is this clear?
Yes, sir.
Okay. Okay. So now we can define a map rho. First we define a projection map. So define the projection now, pi. This is a nearest point projection. Pi goes from n tilde to I of n. So it's just any point in the neighborhood n tilde is of the form Q plus W. So map this to Q. Okay. Yeah. So this projection, what one can show is that this point Q actually is the closest point to this point Z. Okay. So this point here is Q. This Q is pi of Z. All right. Is it clear? Yeah. So you just take the unique line segment from Z passing through Z, which meets the submanifold at right angles. Okay. This will be the closest point to Z in the submanifold. Okay. So this map is well defined by because we have this diffeomorphism phi here, right? So any so what you're doing is you're taking the inverse of phi and then taking the projection onto the first factor, right? Okay. Yes.
Yes, sir.
Okay, fine. So we have this, and now define also another map, rho from N tilde to RQ. Z goes to Z minus pi Z. Okay. All right. So any Z I can write as pi Z plus rho Z, where this rho Z from the definition, this pi Z basically this is equal to some Q in IN, right? And this rho Z, this belongs to the orthogonal complement of the tangent space, right? Okay.
Sir, sir,
Yes.
so this pi you have written, if I take n as S, right?
Sorry, if I take
N to be S2 or
yeah,
Sn,
it's just
radial
Z
projection,
Z
right?
over
X mod.
Z over norm Z. It's just Z
Yeah.
goes Z over norm Z. Yeah.
Yes.
That's,
Yes. Okay.
that's right. Yeah. It's just radial projection in that case.
Okay.
Yeah, but this is well defined using the tubular neighborhood theorem, right? Yeah, what I'm taking phi inverse and then projecting to the first coordinate, right?
Yes.
Okay, that's the map. Okay. Is that clear?
Yes.
Okay. So now any Z I can write as pi Z plus rho Z. This pi Z is the Q and this rho Z is the W. Okay. Yeah. Okay, so let's note this so that the identity map is equal to pi plus rho. Okay. So so maybe I should note this. So therefore, if I take derivatives, I get that identity is equal to d pi plus d rho. Okay. And if I take second derivatives, so nabla of this identity, this is actually the derivative of the identity. I'll get, so the second fundamental form of the identity is 0, right? From RQ to RQ, because it maps geodesics in RQ to geodesics in RQ. Geodesics in RQ are just straight lines. Straight lines go to straight lines under the identity. So the second fundamental form of the identity is 0. So that implies that 0 is equal to nabla d pi plus nabla d rho, right? Okay. So we'll use these formulas later. Is it okay up to here? Yeah. Yes.
Yes, sir.
Okay. Now notice that so pi goes from where to where? From n tilde to I of n, right? So that implies that d pi at any z, it maps RQ into the tangent space to I of n, right? Yes? Okay. And rho z belongs to the orthogonal complement of the tangent space. So that implies that the inner product between d pi z of W and rho of Z, this is 0 for all Z in n tilde and for all W in RQ, right? Okay. Yes.
Yes.
Okay, fine. All right. So also let's make some more observations. So notice, so since I from N into RQ is an isometric embedding for any geodesic gamma in N, I of gamma is a geodesic in I of N, right? Okay. So thus, if V is equal to gamma prime 0, this belongs to say some TPN. Okay. So then the second fundamental form of I, nabla di at P acting on V comma V, what is this? This is capital D del T at T equal to 0 of ddt of I composed gamma, right? Of T. Yes? Yes? Second fundamental form is the derivative, covariant derivative along geodesics, right? Yes?
Yes, sir.
Okay, so what is this covariant derivative of, so this capital D del T what is the covariant derivative of for a submanifold? This is equal to the usual derivative, and then you take the tangential component, right? Yes?
Yes, sir.
Okay. So this is equal to I compose gamma double prime 0 tangential component, right? And this so since I is an isometry from yeah right, so wait, let me just be careful of 1 second. Yeah, okay. Okay, so no, I have to be a bit careful here. So, okay. No, so, okay. Yeah, so. No, I was mixing up two second fundamental forms. So we have to be a bit careful. I is a map. So you can think of it as taking values in the submanifold I of N, or you can think of it as taking values in RQ, right? So I want to think of it as taking values in RQ, all right? Okay. So the second fundamental form will be a bilinear form with values in RQ, all right? I want to think of it like that. So then, okay, so I compose gamma as a geodesic. So that means that if it's a geodesic in the submanifold, then that means its tangential component of its acceleration is 0, right? Okay. So this implies that I compose gamma double prime. This belongs to the orthogonal complement to the tangent space to the submanifold. Okay. Yes. Okay. And this nabla di at P. So here this Q is I of P. And this gamma 0 is P in M. Yeah. Okay. So this second fundamental form, this is going from where? This is going from TPN cross TPN to RQ. Okay. So this is given by, so second fundamental form, nabla di of P acting on V comma V is I composed gamma double prime of 0, where V is equal to gamma prime 0 in TPN. Okay. And so this therefore belongs to the orthogonal complement of the tangent space. Okay. All right. Yes, is this okay? Yes.
Yes, sir.
So be careful. The second fundamental form, I'm looking at I as a map taking values in RQ. So therefore, the second fundamental form will be given by the covariant derivative in RQ of I compose gamma prime, right? So that the covariant derivative in RQ is just the normal derivative, right? So this will just be the normal second derivative of the curve I compose gamma. This is a curve in RQ. So I'm just taking its usual second derivative. Okay. All right.
Yes, sir.
Okay. So what does that tell me? That tells me that the second fundamental form of I, it takes values in the orthogonal complement of the tangent space to I of n. Okay. But now notice if Q belongs to I of n and W belongs to the orthogonal complement of the tangent space, then pi of Q plus TW is just Q for all T small. So that implies that d pi of the orthogonal complement, yeah, so d pi of d pi z of W, this is ddt at t equal to 0 of pi of z plus tw. This is 0, okay, where W belongs to TQ IN perp, and Q is equal to pi of W. Okay, so this tells me that the projection, it maps the orthogonal direction to 0, the derivative of the projection, right? I mean, that you can see in the picture here. Yeah, in the orthogonal direction, this map is constant, right? So the derivative maps the orthogonal direction to 0. Okay. So that tells me what? That tells me that this second fundamental form, it takes values in the orthogonal direction, and the derivative maps it, derivative of pi maps the orthogonal direction to 0. So thus, now I can use the following fact that the inclusion I can write as I as pi composed with I, right? So by the composition formula, I get that the second fundamental form, nabla di, what is this? This is d pi. Well, okay, let me write it this way. So it's nabla d pi of di comma di, right? Plus d pi of nabla di, right? This was the composition formula. Yeah. But now this d pi of nabla di, this, as we've seen, this is 0, right? Because nabla di takes values in the orthogonal complement, and d pi maps the orthogonal complement to 0. Okay? Is this clear?
Yes, sir.
Okay. So I think now we can relate solutions of the harmonic maps heat flow to solutions of a PD, a nonlinear PD in RQ. Okay. So now let U from M cross 0 epsilon to N be a solution of the heat flow. Okay. So let U bar equal to I composed U. So this is now going to take values in RQ, right? So we want to see that this satisfies some PDE. Okay. So so for the heat equation, we need to look at del U bar del T, right? So this is del T of I composed with U, right? So this is by the chain rule di of del U del T, right? Okay, fine. And now let's look at the Laplacian of U bar. So what is the Laplacian of U bar? This is the Laplacian of I composed with U. So this is the same as the tension field. Since this is a map taking values in RQ, this is the same as the tension field of I composed with U, right? And that by the second composition formula, what is this? this is so the trace of nabla di of du comma du, right? Plus di of tau u, right? Yes. Okay. Right.
Yes, sir.
Okay. Now, what is this trace of nabla di of du du? So here, now we go up and look at what we had earlier, that let me just see 1 second. Yeah, so nabla di is nabla d pi composed with di, right? So I can use that here. So this is trace of nabla d pi, and then I'll have di composed with du, di composed with du, right? Plus di of tau u, right? So this I can write, this di composed du by the chain rule, it's d of I composed u, which is d of u bar. So this becomes trace of nabla d pi of du bar plus di of tau u. Fine. So now I subtract these two equations, right? So what I'll get is that del u bar del t minus Laplacian u bar. This will be minus trace of nabla d pi of du bar plus, then I'll have this di of del u del t minus di of tau u. So I'll get di of del u del t minus tau u. Right? Okay. So this del u del t minus tau u, this is 0 because I'm taking a solution of the heat flow. So finally, what do we get? So so this thing here, this is a bilinear form, right? This is a this nabla d pi of du bar, and then I'm taking its trace. So let me define. So define pi. This is just a notation. Pi u of du comma du. Define this to be trace of nabla d pi of so pi u bar of pi u bar of du bar. Define this to be trace of nabla d pi of du bar. Okay. So what is this thing? This thing is this pi u bar. So this is a map from M into R cube. Okay. This is a map from M into R cube. So thus we get thus U bar from M cross 0 epsilon to R cube satisfies the PD So this PDE, where this last term vanishes. So let me write it in this form. It's a nonlinear heat equation. Del U bar del T equal to Laplacian U bar minus pi of U bar du bar du bar. Okay. So this first part is like the heat equation. And then there's this nonlinear. This term is what? This is a nonlinear first order differential operator, right? Okay. Yes.
Yes, sir.
Okay, so is the derivation clear? Yeah. Okay. So we proved one direction, that is, if U is a map from is a solution of the harmonic maps heat flow taking values in N, if I compose with the isometric embedding into RQ, then I get a solution of this PDE, right? This nonlinear heat equation. Now, what I want to prove conversely is that if I start with a solution of this PDE, and suppose at time 0 it takes values in N, in I of N, then in fact it comes from a solution of the harmonic maps heat flow. Okay, so let me call this equation something, double star. Okay. So proposition, if U bar from M cross 0 epsilon into N tilde, which is the neighborhood of I of N, is such that one U bar of x comma 0 belongs to I of N for all x in M, and 2 U bar satisfies this PDE star then there exists a solution U. So U bar is equal to I composed U for some solution U of the heat flow. Okay. So U goes from M cross 0 epsilon to N of the heat flow. Okay, is the statement clear? Yeah, so this is the converse.
Yes, sir.
Okay, so we'll prove this next time. We're out of time now. So we'll prove this on Friday. Okay. And then the idea is we'll use this to prove short-term existence of the heat flow by proving short-term existence for this PDE in Rn. Okay, and there we can use properties of the heat equation in Rn. Okay, that's the idea. Okay. Okay. So let me stop here and we'll continue on Friday.
Hello, sir.
Yes.
You were telling in the last class that you would shorten the syllabus for the interim exam.
Yes.
Can you please send out an email, referring the details that which notes should we follow explicitly for the interim exam? Among all your notes that you have put up on the Google Drive.
Well, just follow